Welcome to our final lecture of data structures and algorithms in C++. This is going to be a revision lecture and a chance to consolidate all the material that we've covered over the past weeks of this curriculum. So let's just walk you through those points and talk a little bit about the key aspects of these weeks. So obviously in the first week we had our warm-up week. We were just covering the fundamentals of C++. A lot of you had done the introductory C++ course, so this came naturally and easy to you, so that's a good sign. We were just taking this opportunity to warm up, covering all the aspects of object-oriented programming, and having a look at some key tenets of C++, such as pointers, templates, memory allocation, as well as a standard template library, which of course we then went on to have a look at how some of the data structures and algorithms are incorporated into that standard template library and how our implementations will could be similar or different in some places to those STL libraries. So that's where we started. And then in the second week, we contrasted the array, which we probably would have mentioned in that first week, the standard primitive type arrays, such as an integer array, a character array, which we know is a string, and other types of arrays of objects, perhaps, as well, of a class we may have created in the first week. So we had a look at the index structures, such as arrays, and might have also mentioned vectors at that point as well. That would have been a good opportunity, with lists, which are typically reference-based. And we would have had a good look at the singly linked lists and doubly linked lists, which are connected by pointer. And of course, that's explicit in C++, where that might be more implicit in other languages like Python or Java. So that was our second week. And then in the third week, we covered the key ground of computational complexity, like big O notation, primarily having a look at the different categories, different classification of algorithms. And indeed, we'll remind you of those in this lecture. I had a good fun of playing around with different searching and sorting algorithms, binary search, linear search, merge sort, and bubble sort, probably sequential sort, and had a look at the different categories there. And then in the fourth week, we covered hashing, which we primarily focused on the two main types and two main ways to resolve collisions, which is important. Of course, in a nice ideal world, there wouldn't be any collisions, but in the real world, there are collisions with trying to condense down unique hash codes, which are typically quite large, depending on the algorithm, especially if they originate from the ASCII codes, and as they are multiplied by their position. Quite a lot of the hashing algorithms start there. Obviously, they end up being these very large numbers, and we would perform something like modulus on them. In most techniques, it's the foundation of most hashing algorithms, to condense that down to a finite number of spaces in a hash table or hash map, which has 30 spaces to start with, if it's a fixed size table. Obviously, we will eventually come across unique numbers, but which, when condensed, will end up with the same index position within our table. So we had a look at ways of resolving that by having chaining, so having a linked list, or open addressing, where we find other places in our data structure to be able to store these colliding elements, let's say. And then in the next week, the week 5, stacks and queues, again, fairly, well, I'd hope they'd be elementary data structures, but actually very useful because they have lots of applications, both with other algorithms, as we saw later in depth first search and breadth first search, and of course model real world in terms of queuing up, if we're queuing up to get the bus, the flow of traffic, traffic queues, stacks of delivery boxes, stacks of plates in a restaurant, all these types of things. They do have a lot of real life application and model scenarios. So actually quite useful in their own right, but definitely a foundation for some of the later topics, which indeed we get onto when we looked at trees. So we had a look at arranging nodes, items within a tree-based structure, which is obviously hierarchical. You'd start with a root node and then have levels layers of these nodes. Those could be ordered in such a way as like a binary search tree, which has a particular set of rules, a left child and a right child of the parent node. The left has to be less than the root, and the right has to be greater than the root. That's quite a important arrangement for implementing binary search in logarithmic time. So I had a look at that. There's a challenge as well to have a look at a self-balancing tree and AVL tree. And also we had to look at just, modeling folder directories. Again, a common application, isn't it, to have nested folders and how that could be mapped out in a tree. And indeed, sometimes you can model binary search trees with an array as well. You can actually, if you store them in the correct positions, you can actually store them that way and then filter by that, especially if you have a divide and conquer algorithm as you progress down to find where they're located. Okay, so that's trees, which is all concerned about the arrangement of the items within the tree. Graphs are, would look similar to at least the pictorial diagram of a tree with nodes connected together. Typically, obviously, it starts in a sort of tree formation. Graph, could be laid out in any particular way, but those nodes are still connected. But the key difference between graph and tree is that with graphs, we're more concerned about the distance between nodes. We actually assign, in graph theory, we would call those nodes vertices, and the connections between them would be referred to as edges, and typically would have a weight given to that, so stored as a value. Could represent any given unit. It could be time taken to travel between those nodes, or the distance, miles, kilometers, meters, whatever. Or even in network flow, it could be just total capacity that channel has between those two locations. So we had a look at navigating graphs. So of course, a bit of work to set them up in the first place. So actually, once we've got them set up, then actually having a look at creating them and navigating them. We can apply breadth first search and depth first search again here. Making use of stacks and queues like we just mentioned. And then graph path finding. Yeah, so that's part 2 of graphs. That was actually applying named algorithms like Dijkstra's algorithm. And there's several others as well, like Bellman-Ford, typically for negative weights, which Dijkstra's doesn't always, the original one doesn't cater for, unless you modify it. So that's like a modified version of that algorithm. Bellman-Ford, and there's many others as well. The Floyd-Warshaw algorithm, that's an example of a dynamic programming algorithm, which we'll see in a bit. And there's even ones like A star, which use a heuristic, which actually have heuristics like as the crow flies, or Euclidean, as we usually refer to that, or something like a Manhattan. If you've got a grid-based space, like the area of Manhattan, or Barcelona in Spain is similar as well, but the distances between blocks or roads are of equal size, and it's all laid out in uniform distances, then we could adopt that sort of heuristic to know roughly how long it should take. It's basically like an estimate, prior knowledge that we integrate with our pathfinding, so that we can really measure against it to know whether we are kind of within that region that we're estimating, or whether we've gone wildly off track and we can discard that path because it's gone, it's not what we'd think it should be, that path time that it should take. Okay, and then of course our last week, penultimate week, dynamic programming. Have a look at a variety of different techniques, actually, from optimization algorithms to do with obviously it lends itself very well to recursive problems which require recursion, such as Fibonacci numbers, factorial numbers. There's also the famous rucksack problem, or it's usually referred to in American textbooks as the knapsack problem, trying to find the optimal number of items that will fit within a fixed capacity. And each item's got its own weight and its own priority, and that. So that's an interesting optimization problem, which dynamic programming lends itself to. So there's optimization problems. There's also string-based problems. The longest common subsequence is one of the more famous ones, and of course graph programming, as we talked about with Floyd-Warshaw. So that's just giving you the course curriculum as it is. Let's just expand on those points a little bit further, week by week. Okay, so let me just take you through these slides here. So first week, arrays, yes, as well as the C++ fundamentals. This was also an opportunity for us just to recap on arrays, which are usually covered in introductory courses, and definitely one of the building blocks that we then went on to work with all of our other algorithms. So an array, just to remind you of what you already know, uses indices. These are numbered positions. They're auto-incremented, so we start typically at 0. In most programming languages, the first element is 0, and we then increment that number. So each storage area within this block typically contiguously allocated. An advantage of that is speed of navigating the structure. If we specify up front how much memory we require, and that's typically just a multiplication of one type, hence why they're usually statically typed. If we defined of one primitive type, like an integer, if it's a 32-bit integer space, that would be 4 bytes. So they would all be 4 bytes apart in memory. And again, you can use pointer arithmetic to actually get to positions within the array. And the array itself holds that first memory address. And then, of course, pointer arithmetic is the back end. And we use loop counters as well at the front end to be able to navigate this structure. To get to numbered positions within it. Okay, so that's for a fixed size array. Homogeneous data, the advantage of that obviously is that we can have that speed of access. Access is constant time, so obviously if we know the index, we can go straight to it, and that's exactly the same regardless of the size of the array. There's no overhead to actually have to iterate through the array to actually get there. No, because it's indexed, every position has been mapped out, we can go straight to it. So when the index is known, we go straight there. However, if it's if it's not known, of course, we have to go about finding it, ascertaining it. So a number of approaches to that, which we go on to explore, obviously. Linear search is linear time. So that would just be iterating from the start until the end. Potentially you could make some efficiency if you have 2 pointers and you search both ends into the middle. That might speed up the amount of time from going from one orientation. So that's linear approaches, or you might find a more linear arithmetic, n log n, or even in this modern day some more efficient algorithms which have some space savings. Something like a divide and conquer algorithm would be n log n, like merge sorts. So we went on to have a look at that. Okay. What are some of the downsides with arrays? Well, I mean, if we have to shift the numbers, that obviously has a cost. So the placement of those numbers might be important. If we have to basically shift the elements by 1, that's going to have a linear overhead because we have to have a temporary kind of allocation as we then overwrite the other ones to make space for one which has to be put either in the start of the list or in the middle of the list or somewhere in the list, which requires others to be moved on or be moved around. So there's a little bit of an overhead there. It's not quite as easy as a linked list. Obviously, that's one of the key advantages of a linked list, which I think we're about to go on to, is that because it's pointer based, we can quite easily just change pointers without disrupting the rest of the list. So let's go and do that. So let's talk about this. This was our second week, wasn't it? It was comparing the index-based structures, the arrays and the vectors, which can be achieved through the standard template library, with a linked list. That could be a list in a STL library, or we even had to go creating our own. We had a linked list management class. And we had a node class which managed the pointers, as you can see from this illustration here. That was we got a singly linked list here, haven't we? So we're pointing one way. So we have a head, or first, as it's sometimes known, the first in the list, which has a pointer to the next one in the list, has a pointer to the next one and the next one. And that might end up with a null pointer at the end, or you might use a different value potentially. Depends how strongly typed you are, how type safe you want to be, whether that's 0 or null or something else, all to be decided, and varies across languages. But definitely having something at the end to recognize we're at the end of the list, whether that's null or 0 or otherwise. Okay, so we keep repeating until we get to the end. Or in fact, it's sometimes advantageous to have a tail pointer or a last pointer, as long as you update it every time you change the list, especially if you're adding at the end, you need to move it on, so that you don't have to then iterate to get to the end of the list, especially if you are appending. adding to the end of the list. Prepend is easy because, of course, you just add it to the first. You make the old first, the next of the new first, and that's something we had to go at. So prepend can be done in constant time. Yeah, append without the tail. Obviously, we have to iterate to get to the end, and that could be linear time, depends on the size of the list, how many nodes are in the list. We've got the tail, obviously, we can do that in constant time. As long as we've got everything updated, got a pointer to the end of the list, we can go straight there, and we could put it there. Okay, so I mentioned that it's a lot more straightforward to add things mid-list within a reference-based structure, as we see here. That's one of the advantages if we're going to have a lot of removal or even addition within the sort of center of the list. Depends what it's storing, but as long as we make sure we don't lose the rest of the list, that's, with good algorithms, we wouldn't. We just have to make sure we don't, especially if we're removing, we make sure we assign the remainder of the list to the next of the one before the one we're about to remove. So we don't delete the one which holds the next pointer to the rest of the list, and then we lose that. So we need to make sure that we've changed the pointers before we then remove them. Okay, so one of the downsides of lists, of course, is it's usually not indexed, otherwise it would basically just become an array. So we usually don't maintain indices for the items of a linked list. So potentially not so helpful for large lists. You might want to think about something that is indexed if you need to get things in the middle of the list, but it does have that flexibility which we just mentioned. So from head and tail, it will be linear time, general average case, to be able to get to items in a reasonably sized list. But yeah, just be aware of that. So there's different advantages and disadvantages, and obviously context matters, application matters. So this is all part of the course, is raising those questions regarding, where they best suited and what context do they fit in. Hopefully you've had a chance to explore that, and if you're using them in your coursework, then hopefully you're appreciating that and hopefully discussing it in your work too. So, okay, now that we've covered the difference between the reference-based structures and the index-based structures, let's just remind you of these classifications of algorithms, and we're assisted very helpfully by this diagram here, which I think nicely plots the number of elements on the x-axis against these operations, the number of operations, or you could also equate that with time it takes to perform those operations, which we had to go at, didn't we, this week? We timed how long things took. You could also, keep account of how many operations are done, how many reads and accesses and assignments are done in your loops. But here you can see, quite clearly how these functions grow according to scale. So it's plotting the growth of functions in comparison with their size. So obviously constant time O of 1 doesn't change, and O of log n, logarithmic time, scales very well. So I haven't got it here. One of the things I would so it's logarithmic. It's the inverse of the square root. So it would be the the inverse of the square, which would be the square root. So it would be something like so the inverse of the squares, which would be let me just say it again. Which would be the inverse of the power required to multiply a number by the exponent there by, so for example, 2 cubed would be 8. So logarithm of 8 would give us 3. So that would be the number of times, number of levels we'd have to divide by to get to it. So obviously, if you do a logarithm of a very large number, you'd actually get a fairly small number. I seem to remember like 8,000. The logarithm of 8,000 elements was about 12 or something like that, and then and then as you increase it from there, it doesn't change too much. It obviously does increase in line with it, but shows you that if you visualize that as a tree, they would plot out in just levels essentially, and that's where we achieve the logarithmic search time, especially when we get to binary search trees, and you may have applied binary search here. Providing you've got it sorted, of course, because every time you discard half of the list, half the tree, half of the data structure, if it's sorted in that time. So that's one of the advantages of binary search and the binary search tree. So that's logarithm, and we also have OFN. We said linear time. That's directly proportional to the size of the data structure. So I don't know, for example, let's say we're trying to read an array. If we're just trying to display the elements stored in the array, if it takes 5 milliseconds to read and access and print out the elements, each element of the array, that would be 5 times the number of elements we have. We have 5 elements in the data structure. That's 25 milliseconds, and then obviously that will just grow in proportion to the size of the structure. So that's an advantage. That scales fairly well. That's usually a good rule of thumb here, is that a single for loop, a single level of a for loop would equate to linear time. Obviously, average case, assuming that you're reading every single element of this data structure, one loop would be proportionate to the linear time, because we're navigating through every element of that data structure. And then obviously, if you've got a nested loop inside that, if you've got an inner loop, another for loop, or another type of loop in there, two loops, an inner loop and an outer loop, that would be O of n squared. As you see there, in the red category, quadratic, O of n squared. So obviously that scales much faster, because for every element we have to perform another loop for each one of those elements. So that's O of n times n squared. So you can tell the difference between those two, how sharply this one increases compared with this one. So there's a major difference between the levels of loops, and of course O of n to the power of 3 is even steeper. So yeah, that's definitely something we explored during this week. Linear search O of n and bubble sort and selection sort were classified as O of n squared, because they generally have 2 loops in them, in an inner loop and an outer loop. There are efficiencies, there are kind of optimizations you can make within that space, but generally if you've got 2 loops, it's usually going to be within that classification of algorithms. Okay, and then we did actually have a look at merge sort, which is a bit more involved, but does come out far more efficient. It scales better, not quite as good as log n, because it's n times log n, so you multiply those 2 together. Logarithms for every n operation. So that's an example of merge sorts, where essentially we divided the parts of the data structure up and then merged them back together in sorted order. So that's a good one to have, very useful on larger data structures, and scales better than a quadratic sorting algorithm. So it was good for us to play around with different sizes of data structures to see exactly how long they took, or you might have printed out a number of operations as well. So there we go. That's just a key point of this week 3, complexity. Let's move on. Let's have a look at hashing. Okay, so as mentioned, there are 2 separate approaches for resolving collisions. That was the central focus of this week. Living in the real world, trying not to be too idealistic. We're going to encounter collisions. As good as it is to generate these unique hash codes, you can see from the animation here that we calculate this very large unique hash number, but the problem is when we perform modulus on this large number, we do end up with a smaller range, and we're most likely to have overlapping or colliding elements. So we have to then resolve that in some way. We have to work out which one of those elements we want to refer to by that hash code. So we could do that via a linked list, a sort of reference-based structure, which we use the unique index to arrive at that space, and then we just iterate basically in a sort of linear search fashion until we find the colliding element. Hopefully we haven't got too many collisions, because that might tell us something else. Maybe we've not done this so well, especially if all the other elements are empty and there's only one element which is being taken up by a huge list. Well, that's basically a linked list, isn't it? So we'd have to rearrange our hashing algorithm to be a bit more optimal to fill up the rest of the spaces. So that's our chaining. And then the only other, then the other ones, other school of thought that we looked at was this open addressing, trying to find an empty space, whether that's linear probing, literally just iterate until you find an empty space, or quadratic or prime intervals. And we had a look at playing around with how those work and how they would be advantageous or disadvantageous depending on the size of the structure. Okay, so obviously, in an ideal world, if you've got every space build up without collisions, the access is great because you've got constant access to the elements. You would translate the key into the index value and arrive at your value that you're seeking to get. But of course, that's a bit too idealistic. We might not achieve constant time. We might have to factor in additional time to either navigate through the linked list or to then iterate through to where we've saved it. Okay, so that's an interesting week this week 4. Okay, so there we go. Lots to discuss there. Let's talk about queues and stacks. Let's start with queues and modeling this first in, first out arrangement. We would typically join from the back of the queue, or let's say we have an empty queue. If we're the first one in the queue, as modeled here, we are the first person to be served in generally in the queue, or advance, or whatever the situation is. So that first item in the queue is the first one out of the queue, and obviously items join from the back of the queue, and then they back up from there. So that's the arrangement. We could model that in terms of arrays. If we've got a fixed size array, one of the advantages we could employ would be pointers. We could actually have a circular queue where, if we're dealing with fixed size arrays that we can't expand and contract so readily as we would a linked list, perhaps a little bit easier with a linked list, adding and removing. But with fixed size array, we could still have those pointers of a linked list and just manage those as we add to the queue and remove from the queue. So that's sort of a hybrid approach there with a fixed size data structure. Okay, priority queues as well. We might cover this, might have had a look at this in terms of just assigning weighting, and that's adding a sorting element. So that's actually arranging the queue by priority, either ascending order or descending order, depends on which one we value or how we're going to arrange this queue. That could be, think of this in terms of work tasks. You might arrange that by order of priority, whether it's urgent, important, medium, not so important. That would obviously affect the ordering of how your tasks are allocated and which ones you need to solve first. So that's a real life application. And then, of course, as we said, we would then go on and apply queues with breadth-first search, either with trees or with graphs. So you can see the animation here, the GIF, that because of how the queue adds items and removes items, it lends itself nicely to exploring the breadth. So you can see that A was added first, and then its children B and C were added to the back of the queue, and then in this case, it's flipped, by the way, just to let you know. It's obviously the front is at the right-hand side and the back of the queue is at the left-hand side as in terms of how it's removed. So there we go. B and C are added in that order, and then B is served and its children are added, and then C goes to the front of the queue and its children are added to the back of that queue. There we go. So that lends itself nicely to modeling the breadth as opposed to the depth. So making sure we cover all the children of each level before we move on to the children of the next level. Okay, and we're going to see that with the reverse of that with depth first search. So we'll come to that in just a sec. So with stacks, it's a different arrangement. That's modeling, I think of like a stack of books or a stack of plates. We're not going to be pulling the books out from the bottom unless you're like a magician or something. But generally, for those of us who aren't skilled in that way, we would stack them up on the top, and safely we'd want to save our plates and our books or our Jenga or whatever. We'd remove from the top. And so we add from the top and we remove from the top. So that translates to the last one added to the stack is the last one. Oh, sorry, the first one to be removed from the stack, first out. Okay, so we had a look at playing around with this in terms of the using an array, or could also use a linked list, could even combine two to get a linked stack. There's a number of different orientations we could use. Key advantage of this data structure is that it's always constant time because it's always the same element. Top, we only have to have one pointer, and we add to it and we remove from it. So constant time for that, which is quite useful. Good to have that consistency and that assurance there. It's, as we mentioned, this is applied heavily with depth-first search algorithms. Let's just see the animation here. So A is added, stacked up, then it's removed, and then stacks up its children, B and C. But if we're going to pursue B, the children of B are stacked on top of C. So remember, we add and remove from the top. So we're going to service D and E, the children of B, before we get to C, which is sitting underneath those. It's not being served because it's at the bottom of the stack. So that, again, the way it's set up lends itself nicely to pursuing depth of a search space, a tree, or a graph, or something, because of its setup. Okay, so there we go. That's stacks. Let's now talk about trees. Okay, so here we go. We see a diagram of a tree. And here, I think we're modeling a binary search tree, looking at the numbers. So the key thing about a binary search tree, a BST, of course, as mentioned, is that the root node that is central, that's the first one, and the left children of that root node must be less than that root, and then the right children must be greater than that root. This allows us to have that logarithmic search capacity where we can discount one half of the tree at the time. So obviously that filters down the levels. We then go to the next level, check the parents, check the children, and then the process repeats in this sort of, it could be done recursively, it could be done iteratively. It lends itself nicely to recursion, but recursion not always the most efficient. So as we'll see with dynamic programming. Okay, so there we go. That's the BST, and AVL. That's the self-balancing tree. A little bit of a step up. That was a bit more of a challenge for us looking at that. And then red and black float tree is again just looking at the balance of the tree, assigning some row nodes to be red, some to be black, and trying to have that symmetry between them. So many different types of trees. There we've covered the advantages and the key parts of the binary search tree. That's a good one. We also had a look at folder structure as well, didn't we? Again, a real life application of these trees. Very useful. Stuff we do every day, isn't it? Is navigating file structures on our devices. So a common application of this data structure. Okay, let's talk about graphs. So with graphs, as mentioned, graph theory tends to refer to nodes or links, we might refer to them, some placeholder term, with vertices. So these nodes we'd refer to as V for vertices, or vertex. And then the connections between them, the weights that we assign to the cost travel between these vertices, vertexes, are edges. And the weighting that we well, first of all, they don't have to be weighted. They could all be equal. They might all have the value of 1, which means there's no real differentiation between the time taken to get between these. It's actually more interested in connections rather than the time taken. That could be an unweighted graph, or we could have a weighted graph, as you see here, where the values are different, the edge weights are different, and you notice that we don't always have a route back. They're actually directed. So this is meaning that it would take 2 meters, 2 minutes, or whatever the unit is, to get from A to B. But notice there's no route back from B to A. Otherwise, we would, we'd have another we'd have an arrow at the other ends pointing back to A, or potentially, again, depending on geography, depending on what you're trying to model, you might even have another route which could take longer, could be shorter to go back from B to A. So there's all kinds of different ways of writing these. But yeah, in this case, we would have a directed graph, and it's a weighted graph, so you can have lots of different combinations of those. Weighted, not weighted, directed, not directed, to be explored those, just getting a graph set up. Of course, I have cycles in a graph as well, so if we do actually have a way back from C to A, we could potentially get stuck in a cycle. We may never, if we keep navigating from there to there, that will infinitely regress. So we need to be careful of that. Especially for pathfinding when we get to that. So it's obviously useful try and detect those cycles in a graph, because that will mess up some of our path algorithms. So we had a look at setting up. We also had a look at, how we could set it up. Again, there's like most things, there's multiple schools of thought here. Generally, two main approaches. You could have a reference-based structure, like a linked list, where, well, these nodes, these vertices could be stored in an index-based structure, but they could they could actually store the connections, the edges that they connect to, as a linked list. So that would be an iterative approach to iterate through each one of the stored vertices, A, B, C, D, E, F, G, in an index-based structure, and then the links that they the connections they point to. Okay, so that's obviously access, is a constant time to get to the starting vertex, but then to actually navigate that has a cost. That's the number of edges, vertices and their edges to actually iterate through that, and applying our breadth first search and our depth first search algorithms. That's in a reference-based structure. Alternatively, you could store it in a 2D matrix, a 2D array, combination of those two, a vector which holds arrays, or something which basically looks like this 2D grid of rows and columns, where you'd have A, B, C, D, E, F on the columns, and then again on the rows, and you would just store at that point these values there. So that's obviously constant time, and to actually navigate that with breadth first search and depth first search, that has a quadratic or V times V approach to actually navigate over those. So yeah, two schools of thought there on how to set up a graph, and we had a look at that. And you can even use other standard template libraries as well, such as maps and pairs. That's also here. In Python, you can do it as just a dictionary. So there's a number of different ways to store graphs and to model them. But they are obviously highly applicable in many different contexts. So we had a look at some shortest path algorithms, to find either to return all of the shortest paths to each of the respective vertices as a map, or indeed just to return the pathway between a start node and an end node. Might be the focus of the study. So Dijkstra's had a look at that. Usually that works out to be quadratic, V times V. So you can actually make an improvement on that if you use priority queues, otherwise known as min heaps. But yeah, we had a look at the implementation of that, which again has many different variations and many different ways of setting it up. Got to check for non-negative weights though, or cycles, because again that could be a problem. If you do have negative weights, even consider using breadth first search for completely unweighted if they're all equal. For negative weights, had a look at that using Bellman Ford. That was a good alternative for negative weights. We had a look at the A-star algorithm, which is a slightly different application. We need more of a search space. That's probably more applicable to matrices to actually navigate a pathway. And because of the heuristic nature, which they were modeled by variables, F, G, and H, essentially what it's kind of shortened as, it's essentially the Dijkstra pathfinding, or breadth first search, combined with comparing against a heuristic. Either that's Euclidean as the crow flies, as you'd expect it to be from point A to point B, traveling straight there, or it could be Manhattan, navigating the grid structure of, can only move, in a 2D space. We can't move like diagonally or something like that. So we had a look at that with A-star, which again takes a bit of time to set up. That again is a good example of applying all these things we've done until this point, such as stacks and queues and breadth first search, depth first search. It's a good chance to have a look at all these different algorithms that we're using there, factor in the heuristics, and then finally we made moves towards Floyd-Warshall, which is considered more as a dynamic programming style because of its approach rather than the so-called greedy algorithms, which prioritize the sort of short-term win over the sort of long-term checking to see whether there's a shorter path by exhausting all the different combinations. I mean, the problem with pathfinding is that there's a lot of unknowns. The algorithm doesn't know at its current point, whether there will be savings down the line or whether the shortest path is right in front of it. So this is part of one of the perennial problems of NP equals P, that famous debate, whether it's equal or not equal. So that's something to think about. But anyway, Floyd Warshaw getting us close to dynamic programming. Indeed, we went on to have a look at it. One thing to note about that, though, as we mentioned, is that, of course, that has 3 loops. You may have seen the implementations that use it, which, of course, doesn't scale as well. So it may be okay for a small graph like this. It just will exhaustively search. But as that graph and that search space starts to increase, obviously that's going to grow very quickly and take an awful lot longer. So again, those fundamentals come in, and again, with the number of loops that you use will drastically affect how long things take. Okay, so be aware of that. Let's finish up with dynamic programming then. Okay, so again, like most things, there's 2 different schools of thought here, whether you would apply top-down approaches, where you'd start at the top and work your way down. So a good example of this is recursion, as we stack up the function calls. Recursion is a function that calls itself. There's a function call in the return statement of that function. And obviously those calls are recursively stacked. And then executed in reverse order. So as they're added from the top and removed from the top, obviously, that's our stack coming in. So using memorization is essentially just storing it as you go. So rather than having to work it out again, Fibonacci was a good example of this, as we saw, because of the ones later in the sequence rely on calculations in the start of the sequence. We can store those up as we go, so we don't have to keep calculating them again and again and again. We can store them up and refer to that as like a cache to be able to retrieve it faster. So we check to see whether it's in the cache, and if it's not, perform the recursion and store it in the cache. Otherwise, use what's in the cache to work out what we're trying to do. Okay, so that's top down, and then bottom up. By contrast, starts at the bottom, solves the smallest subproblem before then adding to it and building up this table, which is then those smaller subproblems are used to solve the larger problems. Okay, so that's using iteration. We start at the beginning, and as we iterate, we add to typically a table or some data structure, so that we can, solve the larger problems by referring to the things that have been stored in that table. Okay, we could use a map, for example. And that would be in contrast to a stack, as we referred to. And obviously a stack, if it's a fixed size, if it's using an array, it would be a fixed size that obviously will get exceeded at some points, especially if we get trapped in an infinite loop. We don't want to do that. So we need to make sure we've got the base cases for recursion mapped out, as we will get in an infinite loop, and we'll eventually get to Stack Overflow. That's where the form comes from. You know this. So map is a different approach to avoid that function call overhead. Okay, and as we mentioned, there are many different applications of this, from the Fibonacci numbers, were a good place to start, and the rucksack problem, knapsack, all the way up to string processing, which lends itself to this very, very conveniently. And of course, graph algorithms, as we saw. One example of that is the Floyd Warshaw. There are others as well. And we had a look at also some other libraries, didn't we? Like the C++ Boost library for graphs. So we've had a good look at how to code these from ourselves, making use of our own sort of classes, or you might have even gone down the legacy C route of having structs rather than classes, sort of pre-OO, object-oriented programming. And we also had a look at how the C++ library, the standard template library, has these pre-built structures, how we can instantiate them, how we can use them, where they're useful, and where it might be convenient for us to build our own structures as well. So had a good look at a variety of different approaches and different combinations in C++. It's a very rich language to use. So that brings us to the end. Thanks very much for taking this course. I hope it's served your purposes. I hope it's helped you to either revise some of this content if you studied it before or add to it, or if it's completely new to you. I hope it was in a manageable way. I appreciate we had some challenging exercises in there, but maybe now in this last week's a good opportunity to go back to those and see if you can give a bit of time to them, or indeed you might be turning your attention to the final assessments. So whatever you choose to do, I hope this last week goes well for you, and I hope to catch you one last time on the live call and wish you well in person there. So thank you very much for listening. I hope to catch you in the live call. I'll see you there.